and the best fitness will be chosen as the result. Now, I want to mention, as we mentioned before, this aspect isn't so approved by classic GA people, right? Classic GA people do not want you to locally choose the best, because that could create local optimizations, not necessarily global. They like the random aspect. That kick, as we used to call it, is what you want. Even if you think short term, it may seem that the choice that you made was not as good, but that may have a subsequence in it that may be the true answer to the problem. And maybe you need to take a step down in value, in the fitness value, in order to take 10 steps up, because you needed to bump into that little subsequence that's necessary. So, I have to mention that. So, okay. I'm not going to spend too much time on that again, but okay. Classic GA people, classic GA researchers will not be too happy with this approach, since favoring the best during the process is interference with the process. All right. Anyway, so that's their beef, as it were, with this. But okay, we should mention it. Fine, mentioned, but there are people who do it, so hey, we're mentioning it. All right, so let's create a heuristic. All right, yeah. All right, let me think quickly. I don't want to spend too much time. We need some sort of polynomial, for example. I don't want to make 9-term polynomial. All right, let's say I'm going to make a wild heuristic, and let's see how it goes. All right, let's do the following. Okay, let's move this over. So we'll put the heuristic here. All right, let's do a heuristic fitness. I'm sorry. All right, let's see. All right. I'm sorry, because I said I'm going to include both. All right. Okay, let me think. All right, the first 9. Okay, we're going to do the odd numbers raised to some power. Okay, you know what? Let's do it. Let me create it. Let me just write it, and I'll tell you what I did. All right, let me just do it already. Well, you can see the value right now, but 1 second. Where am I up to? 1? Okay. All right, so I took the first position. I'm going to say position here, so you see better. Position 1, position 2, so we can make reference to it. Position 3, let me see if I can drag and drop it across. Beautiful. All right, so what I did was I made a polynomial out of position 1, 3, 5, and 7. Get the heuristic. Creates a degree 3 polynomial out of positions 1, 3, 5, and 7, corresponding to the degrees 3, 2, 1, and 0. All right. So the polynomial is a simple polynomial. The polynomial is, and you could have done anything you wanted. It's x cubed plus x squared plus x to the 1 plus x. Oh, I see. No, hold on a second. Well, that's true. 1 second. is the following. So I have to include the position. Is position, oh, what did I do? Give me 1 second. Did I do multiply? Let me see what I just did. All right, yeah, well, that's what I get. All right, so it's this way. So it's not the same values. All right, the polynomials is the following. Position 1 raised to the third times position 2 raised to the second times, oh, not position 2. It's position 1, position 3, position 5, and then position 7. I realize raised to the 0 does nothing, but who cares? Okay? That's the first part. All right, the first polynomial is this. Second polynomial does the same thing with the evens. So it'll be position 2, which I'll change in a second. Position 2, position 4, position 6, and position 8. Good. So let me see here. I think if I drag and drop it, huh? Curious if that works. I'm curious if that happens. Moved it over. It did. Oh, it worked. All right, it automatically moved over. So this is poly 1. This is poly 2. Oh, so okay, poly 1. Well, okay. Just to make life a little easier for us, what am I doing here? We're going to put the heuristic here. Okay, so poly 1 is the 739. Okay, and that is equal to position, what we said, position 1 raised to the third plus position 3 raised to the second plus position 5 raised to the 1 plus position 7 raised to the 0. Poly number 2 is position 2 raised to the third plus position 4 raised to the second plus position 6 raised to the 1 and position 8 raised to the 0, and although it won't make a difference, the last value is subtracted. It happens to be all the same, but we need a heuristic. Okay, so this is going to be equal to, okay, so let me see what this should be equal to. Let's move this over. All right, so let's move this over. All right, so it'll be equal to the first poly minus the second poly plus the last digit. Again, that has to be constant, but who we don't know. Okay, so here we go. Let's see what happens. All right, here it is. These are the heuristic values for these individual chromosomes. Okay, and who's the max? So the max will be equal to. Give me a second. If this equals max of all of them. So then we're going to put a asterisk. Okay, asterisk, else we'll max. We'll say max. I'm just saying max. Else we say nothing. Okay, let's see if this works. All right, because it's the max. It is the max. Oh wow, my luck. One example. What? No, that didn't work. Okay, give me a second. I'll have to anchor. I'm sorry. If N21 is N21 to N26 max. All right, let's do that again. Yeah, that's it. All right, now, I didn't purposely do it, but it turns out, I wonder why. Oh, yeah, okay, great. All right, so you know what? Let's swap it. I don't know if that makes a difference. If we switch it. Interesting. Maybe if we switch it. Let's see what happens if we switch it. Let's put an M here. Let's do poly 1, poly 2 minus poly 1. What happens? Oh, it does. Right, the smaller better. All right, so this is our heuristic. We want max. Okay, whatever. All right, so what's the heuristic? The heuristic is poly 2 minus poly 1. Fine. So heuristic equals poly number 2. Oh, this is the second heuristic poly. This is the first. I should put it here. You know what? That's not good. I should say second here. And let's call this poly number 1. Let's call this poly number 2. And the heuristic is poly number 2 minus poly number 1 plus position 9. All right. The point is that some messed up heuristic. But it's whatever the heuristic is, I'm going to tell you exactly how to calculate it. And I also have to tell you whether it's a max or a min. But the default we've always been doing is a max. Anyway, so then it would come out that you would choose this. And I'll put a note if, okay, so let's do this. If heuristic were equal to poly number 1 minus poly number 2 plus position 9, then the first chromosome would be max, unless we don't allow, as I mentioned above, unless we don't allow the original chromosome to be part of the mutation. Mutation results. In which case, let's see. In which case, let's see what the other heuristic is. Switched it. Be this minus this plus this. Right, 723, which would have been the max. So then 705. Then the second chromosome would have been. In which case the second would have been. But we are including, well, I would be very clear in the description on an exam, but we're defaulting that it is. In which case second chromosome would be considered, the max. All right. Excellent. All right, so it's busy work because what is the heuristic? It's busy work, as I say. Okay. Any questions on that? Forget Avesh and Walid. Oh, I say. Oh, yeah. No, thank you for your responses. Now I know what. Way back when I asked which are the mutation points. Okay, so that's heuristic mutation. Again, okay, admittedly, this heuristic may have been a little bit more algebraic than you would like, but anyway, it hits a point home. Any questions? That's called heuristic mutation. But please remember, the heuristic mutation must be decided prior to starting the GA. Yeah. All right. Point that out one last time. Oops. All right, good. All right, that concludes our. Oh, yes, okay. So I wanted to mention. What was the case? No. Give me a second, please. Right, okay. All right, so I'll put as a note. Again, no one really does this, but note. Based on this, we could have implemented this as a heuristic crossover. Right? Let's say there are, well, it doesn't have to be regions. It could have been uniform. Okay, meaning, well, except that, okay, so it's a little bit odd because it won't be too, well, it would be a little bit. Now, let me not discuss it. I'll put it as a homework, as it were, that we're not going to go over. I don't want to confuse you. Based on this, we could have implemented a corresponding. Leave it as is. I'm not gonna go over it, and I'm not gonna keep you responsible for it. I just want to mention that this notion could have been applied to a crossover as well. All right, we're done with this. Fine. Next topic. All right. So what I want to do with the remaining time is to talk about genetic programming. All right. Fine. Yeah, that's a good point, Zhang. So here it would be a very good point. Okay, let me write that down. Very good. Excellent point. It would be, then you randomly choose it. That would be the name of the game. If a tie results, then randomly choose amongst the available individuals. Randomly choose amongst the available individuals. Thank you, Zhang. Very good point. Excellent point. All right, genetic programming, also known as, well, not also known as, but for simplicity, GP. All right, so genetic programming is about generating code, so algorithms as opposed to generating solutions, right? That's what we said before. Generating code / algorithms instead of generating solutions. GA. Okay. The other point is that utilizes trees, possibly graphs, utilizes trees as the main structure. Instead of arrays, specifically, more specifically one-dimensional arrays in general, and that is GA. All right, so that's the backdrop. So before we even begin this discussion, we should go into some definitions here. Second. Yeah. All right, let's go through some definitions. Good. So first of all, when you talk about trees, that there are really three main categories or types of trees I like to call in terms of applications. One is a data tree, one is an expression tree, and one is called a decision tree. And they're all the same tree in general, but the way you treat the data in those trees is different. All right. So what's the difference? Okay, in a nutshell, this is a summary, and then I'll give you examples. So in the data, okay, so hopefully you know this. Well, okay, we need some definitions. But we have to remind you from discrete math. Let's go through the definitions, and then we'll go here. All right, so trees. A tree is a graph. Now this is where the definition gets a little funny. A graph G equal to V comma E, right? Where E is a subset of V Cartesian product V, right? Such that, now this is where it gets a little funny, such that, well, there are two ways to say it, such that either a cyclic to unique node termed the root that has a unique pathway to all of its descendants. Now, while this is sort of true, it's not exactly true. This is the way you are led to believe in discrete math. It's not exactly true because it depends what tree, not the tree applications, but what type of tree. It depends what type of graph, really. Okay, is this graph, hence graph / tree, directed or undirected? All right, so if you recall the way we defined it, a Cartesian product is directed. So why is that important? pairs, right? V times V is from the first to the second. So a Cartesian product is directed. The problem becomes that a cyclic is not sufficient. Normally, you would say that a tree must be a cyclic. A cyclic is unfortunately not a sufficient criteria for tree. Why? Because of the following. So I'm just going to save time by drawing this. Give me 1 second. I'm going to draw it, with Excel, it'll be a little bit rough, but I think we could do it. And now, there's a way to do this I found. 1 second, there's a way to do this. I have to remind myself. Phil, no, border. It is border. Okay. Okay, fine. All right. Let me fill in the edges that I'm interested in. Give me 2 seconds. There's a little bit of a problem here. You're not going to know. You're not going to notice this because Excel doesn't allow me to have what you call it. Does not allow me to have. Give me 1 second. Arrows, and directed has arrows. Well, it's not going to be the greatest. The drawing's not going to be the greatest because of the edge problem, the drawing problem, but hopefully you understand what I'm trying to do. Okay, that's a really big arrow, but that's the idea. Notice there's an arrow here. There's an arrow here. Someone has an idea? Yeah, you can draw? Really? Insert a drawing, you mean? Yeah, that's true. All right, anyway, we're almost done. Let's get this over with. All right, so these yellow boxes, these boxes are arrows. All right, so let's give this a name. All right, so this is our root. We'll call this A, and then we'll call this B, and we'll call this C, and we'll call this D. All right, so this is node A. Hold on a second. All right, this is node A, B, C, and D. Okay, is this a tree? Okay. So, it is a cyclic. There are no cycles here. Okay. So it's not a tree. Oh, but no, it is a tree. So it is a, okay, not so. It is a cyclic. Is that sufficient to be a tree? No. So if the graph G is directed, a cyclic is not the issue. The second criteria, B, is the issue. A is not really the issue. B is. Okay? What's B? Let's move this over. B is. What's B? B is the root. Is there, in other words, colon, is there a unique pathway? Is there a unique pathway from A, from the root A, to all of its descendants? No, there isn't. Since A, B, C and A, D, C both go from A to C. Okay? Those are different pathways. This is interesting. So if undirected, it's the criteria B. That's the definition. A unique node terms the root that has a unique pathway to all its descendants. But if you are but if G is undirected, then A is the main criteria, acyclic. Being a root is not significant. Because it's not unique. Now, let's see what that means. So now this clearly, we need more room. Give me 1 second. And we'll eventually get to it. So first of all, if you're, this version would be, we'll have to give it a name. This version here, again, let me put it in undirected, would be a cycle. So first of all, let me say that. And then likewise, I have to make one more comment. And I'll read your comment in a second. Put this in. Oops. Yeah. Good. All right, let's copy this here. Oh, I'm sorry, no. Copy that there. Copy that there. Okay. This undirected version is a undirected version is a cycle. And now, this the above graph is called a DAG, specifically because it stands for something. But it actually is in the advanced graph theory data structure books. It's called graph theory books. It's called a DAG, which is equal to, because that's what it stands for, D for directed, A for A for acyclic, and G for graph. Literally, it's a DAG, directed acyclic graph. Okay, I think there was okay, Andrew says, okay, fine, yeah, I agree. Andrew and Mike, I agree, but I'm just moving on, so let's ignore that. What was that? That's funny. There's a line here, I don't know where I got it. Let me clean that up. Let me get rid of that line. Okay, a little bit cleaner. Now, truth be told, there should be, I don't want to get into this, but in discrete mathematics, well, I don't know, they used to teach us in discrete mathematics, but I don't know if they still do. In discrete mathematics, possibly, so I can't, you don't know this, that's okay. In discrete mathematics, but certainly, or graph theory, certainly in graph theory, it is explained, not or that I don't know, and it is explained that there are multiple, we're not going to get into this, but I just want to make one very interesting point, multiple definitions of graph connectivity. Who is connected to whom? Which vertex connected to whom by which edge? And there are different definitions that are not exactly the same of graph connectivity. Now, according to one of those definitions, the above DAG is actually a cycle as well. Okay, so I leave that as an interesting point, which is, I think you should be aware of, but I don't want to get too much into it. That's real graph theory. All right, so it comes out this way. So now let me show you why I'm saying what I just said, namely that, give me 1 second, what am I saying? What I'm saying is that if you're undirected, root is not significant. So let me show you why I'm saying that. Let me draw this like this. Now I need a little more. Yeah. I think I draw this. That's all. And then it's 2 over. All right. And then let's say one more, and we'll give it different names in a second. I'm going to put in more lines, but okay. So A, B. Let's call this C. And let's call this D. Let's call this E, and let's call this F. Oops, sorry. All right, question. Ouch, sorry. Question on this new graph. Question, very important question. Who is the root? So please, someone tell me, text, who is the root of this graph?